Good morning. This is your stat sensei, Mr. Spensey, and we're going to do two sample proportions and we're going to run a confidence interval. So, Swedish researchers investigated the relationship between chocolate consumption and stroke. So, we're interested in chocolate consumption and stroke. A questionnaire about eating habits was given to a random sample of Swedish men. Based on the responses to the questionnaire, the men were categorized into two categories. Group A consisted of 9,250 men who eat the most chocolate per week. And Group B consisted of 9,250 men who ate the least chocolate per week. It's estimated that at least 2 million men have chocolate consumption habits similar to Group A. The same is true for Group B. The researchers tracked the men's health for 10 years. During that time, there were 458 cases of stroke among the men in Group A and 543 cases of stroke among the men in Group B. Create a 95% confidence interval to estimate the difference in proportions of strokes in the two groups. Well, first off, I'm going to call X1 my Group A, and this is going to be Group B. Group A, this will be B. And we know that both had a sample size of 9,250. They told us that. And we said 458 had strokes in Group A. And 543 had strokes in Group B. So from that, I can get my P hat. So this will be 458 divided by 9,250. So 458 divided by 9,250. And that gives me 0.0495. And here I have 543 also divided by 9,250, and I get 0.0587. All right, so we have two samples. We have two groups, Group A and Group B, and we need to go ahead and define our parameters. So let P1 equal the true population proportion of men in, and I could say that eat a lot of chocolate, but I'm going to say the men in Group A who had a lot of strokes. You know what? I'm going to strike that. I'm going to be more accurate. Of men who eat a lot of chocolate and have had a stroke. I'm going to say let P2 equal the true population proportion of men who do not eat much chocolate and had a stroke. So those are our two groups. Those that eat a lot of chocolate and have a stroke, and those who do not eat much chocolate and have a stroke. Our condition, well, they said it was a random sample, so that was good. So random, both are random samples of 9,250, and that was given. We have two independent 2 independent samples. And that was also given. 3, we need to have a sample size of less than 10%. So N equals 9,250, and 9,250 times 10 equals 92,500, and that's less than 2 million, and that's for both. So I can check that off. And then number 4 is the normality condition, which I consider the most important. So we have N P hat 1, and that one is 0.0495, or 9,250 times 0.0495 N1 P hat 1, and that equals 458. And that's greater than or equal to 10, so that's good. And then we have N1 times 1 minus P hat, which is 9,250 times 1 minus 0.0495, and that equals about 8,792, and that's also greater than or equal to 10, so that's good. And then we need to do the same thing for N2 P2. So N2 P hat 2 equals 9,250 times 0.0587, and that equals 543, which is greater than or equal to 10, so that's good. And then we have N2 1 minus P hat 2 equals 9,250 times 1 minus 0.0587. And what does that equal? And that equals 8,707. And that's greater than 10. So that's good. So far we've met our normality. The samples are large enough. And if I were in AP, I would say, hey, the samples are large enough. All right, we have a really awful long formula. Our formula is going to be P hat 1 minus P hat 2 plus or minus Z star P hat 1 times 1 minus P hat 1 over N1 plus P hat 2 times 1 minus P hat 2 all over N2. Says calculate Z star. So this is going to be an inverse norm area. Well, let's go take a look back and see what type of confidence interval. Well, it says right here that they want us to create a 95% confidence level. So our C level is 0.95. And that's 1 minus 0.95 divided by 2. And we're always, if we have the calculator, it does left, center, or right, we're going to use left. And then we're positive people, so we're going to make it positive. So second vars, inverse norm, 1 minus 0.95, mean of 0, standard deviation of 1, because it's the z-score, and those are always that. So we end up with 1.9599, and like I said, because we're positive people, we're going to write it down as a positive number. All right, we don't have a whole lot of room, so I'm going to shorten these up just a little bit. I'm only going to go 3 decimal places. So this is 0.0495. Okay, I'll go the full 4. Minus the 0.0587 plus or minus 1.9599 times the square root. Well, I'm going to have p hat 1, which is 0.0495 times 1 minus that. And I'm going to go ahead and plug in the 1 minus that. So 1 minus 0.0495 is 0.9505, just because it takes up less room. And put that over my sample size of 9,250 plus or minus 0.0587. That's also over 9,250. They have the same sample sizes. And so 1 minus 0.0587 is 0.9413. All right, so we have our plug. Now we're going to go ahead and run this thing. So stat test, scroll all the way down to letter B. So 2 proportion Z interval. And we have 458 is our X, 9,250 is our N1, 543 is N2, X2, 9,250 is N2, our second sample size, and we have a C level of 0.95. And when we calculate, we end up getting negative 0.0157 to negative 0.0027. So negative 0.0157 to negative 0.0027. And we are 95% confident that the true population that the difference in the true population proportion of strokes in the true population proportion of strokes for men who eat a lot of chocolate versus men who do not eat much chocolate lies within the interval negative 0.0157 to negative 0.0027. Now here's what's interesting. It's negative, and we went, oh, so the group A has fewer strokes than group B. So group A has fewer strokes than group B, and it doesn't contain zeros, so this is statistically significant. All right, so it is statistically significant. I hope this helped. I know there's a lot of writing, and I hope to see you on the next one. Thank you.